No questions? Okay, I was gonna see if let's see if they found somebody to sub for me. Tomorrow, I got called to jury duty. I have to. I have to go. I postponed too many times, so they need me to go tomorrow. But tonight I'll know. So I'm gonna call in. It's at Compton. I get called in, and I have to stay there all day most likely. But we'll see. So what I'm going to do then is I'm going to post tonight if I get called in, and then tomorrow morning I'm going to go. I'm going to try to get excused if I get selected in the morning, and then I'll be back. I think they were trying to get a sub for me for tomorrow, but I'm not sure. I didn't get any announcement for that, and so class might be canceled tomorrow. Just a heads up.
Say if it were to cancel the lab that we're doing tomorrow, we can do next week, or we should skip that lab?
No, you're going to just do it at home. You're going to do it at home because the lab is exercise A, which is nomenclature. Or, maybe I could do a live YouTube if I'm just sitting there, because they make me, at that courthouse, they make people stay. I'll post some kind of announcement. I'll try it in the morning, And what we'll do is we'll just do it, but it depends if you can do that, swing that or not. What it is it's nomenclature. So worst case scenario is I assigned so many nomenclature problems from chapter 6 that you'll have plenty of practice. So if we don't complete exercise 8, that's okay. Some of those are repetitive. All right, so it's a dry lab tomorrow. Just nomenclature. More practice. That's it.
So we're definitely going to need a lab coat for that.
I'm sorry?
So we're definitely going to need a lab coat for that.
Yeah, and goggles. All right, I'm not quite done with nomenclature, so let me finish that up. Alright, so again, if you miss this, class is likely canceled tomorrow. But check Piazza for a current update.
No, my handwriting is really bad, so no.
That's a sign that you want to be done for, right?
No.
No?
Nope.
Lawyer.
Nope.
Lawyer.
Yeah, lawyer. The two professions that have the worst handwriting, lawyers and doctors.
Yeah, right.
Okay, so let's continue on. I'm going to kind of skip most of these slides because your book has a different system for memorizing the names and formulas for this than I presented. You could use either the book or mine.
Tomorrow's canceled. Do we still have to come in and sign it, or
No. Yeah, if tomorrow's canceled, you don't have to drive in to sign the sheet.
Ask if you can live stream the court proceeding.
Yeah, I don't know if they'll let me do that.
They won't let you.
Okay. I don't know if I could live stream from the waiting area.
It depends on how much cell reception you get, and it depends on the rules.
It was the privilege.
But well, we could maybe not do a live stream, but we could do it.
Like a video.
Piazza, back and forth, kind of thing.
Everybody on Skype.
Huh?
Go on Skype.
On Skype.
All right, so there's one last section. We talked about the acids, right, and the acid anions. Acid anions here, like bicarbonate. Right here. Acid anions like monohydrogen phosphate, dihydrogen phosphate. The last section of the nomenclature deals with hydrates. And, an example of that would be this here, CuSO4. CuSO4, what do we call this? Is copper variable or fixed charge? Variable. Can you tell what the charge on copper is based on SO4?
No,
2. And so this is going to be copper 2 sulfate. And that's what we normally call this, copper 2 sulfate. But when you go to buy copper 2 sulfate, they actually sell 2 forms of this. The 2 forms that you can buy are the anhydrous form. And so they call this anhydrous copper 2 sulfate. And then you can buy the hydrated form. The hydrated form would be copper 2 sulfate. Pentahydrate. And so this is it here. This is the copper 2 sulfate pentahydrate. Both of these forms, you know, if you have one, you can convert it to the other without too much difficulty. And so let's take a look at this here. If we look at the copper, this is the copper 2 sulfate. What do we call this? Would this be called a an ionic lattice, a covalent lattice, or maybe a molecular lattice? This would be called an ionic lattice. Do you see the lattice network of the crystal? And it's an ionic lattice because copper 2 sulfate consists of the copper 2 ions and the sulfate ions. So it's shown here. But if you look at this lattice, you know, there's spaces. Do you see these spaces here? There's spaces. So what happens is a water molecule, it's kind of sticky. It gets stuck on the surface. If a water molecule gets stuck in the surface, it can work its way into these voids. We call these void spaces in the crystal. We can see these void spaces in, let's see, other representations. Here it's kind of hard to see the void spaces. Oh, this is quartz, right? It's not copper. Now, what did I do with that? Just do. And so basically it's something like this. This is copper 2 sulfate. It's a different way of looking at it, where waters can creep into the void. We can't fit an unlimited number of water molecules. And so copper 2 sulfate acts somewhat like a sponge, and it can absorb some. In fact, this is the maximum number of water molecules that can be absorbed per formula unit. So if I'm looking at one formula unit of CuSO4, I can fit 5 water molecules. And this stays a solid. It's not wet. It's not a liquid. It stays a solid. And so what does it look like? It looks like, take a look at what it looks like. Here. So on the left, we have what's called the anhydrous form. On the right, we have the hydrated form. When you look at it, both of these look dry, although this kind of looks wet, but it's not wet. You don't see any surface water on these crystals. All the water is absorbed into the lattice itself. And so both of these are solids. This one's just totally dried out, baked out, whereas this one's hydrated. That's the only difference. And we hydrate it to its maximum. Now, how do you hydrate? So eventually what will happen is this one here, that's anhydrous, will hydrate if it's exposed to humid air. You know, and normally there's a lot of humidity in the air, especially near the ocean. And so what we have to do is, in order to protect this, we have to prevent it from being exposed to humid air. Otherwise, it'll just reabsorb all the water. And with time, it just converts into this. Now, if we wanted the anhydrous form, it's easy to get because all we do is take this stuff and bake it in an oven. If we bake it in an oven, then it'll regenerate the anhydrous form. And so these two forms are interchangeable. Sometimes people don't want that water hydration, so they buy the anhydrous form and just protect it. Well, how do you protect it from baking out? Well, you protect it by putting it in a humidity-free container. The humidity-free container usually contains some kind of desiccant. In fact, copper 2 sulfate can be used as a desiccant, you know, because what's going to happen is this is going to suck water out of the air. You know, it sucks water out of the air because water molecules collide with the surface and gets absorbed into the structure. And so this is a desiccant, but it's an expensive desiccant. They're much cheaper desiccants that we can use. Let's take a look at some desiccants here. There's lots of different types of desiccants. This is silica gel, you know, where water molecules get absorbed. It doesn't make a liquid. It just takes the water out of the air. Silica gel. One of the most common desiccants used is something that's inexpensive and it works well. And that's calcium sulfate or calcium chloride. Or let's go by its trade name, Dryerite. This is Dryerite here. This is what calcium sulfate looks like. It's just white solid. Now this picks up water, a little bit of water from the air, and when it picks up water from the air, it still looks dry. You know, and this being white, the color doesn't change much. In fact, it's hard to tell if this is hydrated or dehydrated. And dehydrated we call anhydrous. And so is this hydrated or dehydrated? And so this is the cheap one. In order to tell, you buy the more expensive one. The more expensive one has a blue dye that's added. And so they'll add a blue dye which changes color. And so when it's blue, it's good. This is dry. This will suck water out. And so the air inside here has probably very little humidity compared to the air outside here. And when it starts to suck water, eventually it'll become saturated with water, although it's not going to look it. When it becomes saturated with water, its color changes. It's the color of this. And so blue's good. White, we don't know. White is cheaper, of course, because you don't have to buy the dye. But what happens when it goes bad? This is an apparatus to dry air. You know, with all the gases. And so they force gases through here to desiccate them, to dry them. You know, so if you want zero humidity in your gas, you can dry it this way. As a drying tube. This is what it looks like when it goes bad. You know, so this is the anhydrous form, this is the hydrated form, and it's been saturated with water vapor. But you don't throw it away. We never throw this away. You know what we do with this?
Put it in the oven.
Yeah, put it in the oven and it reverts back to blue. Just drives off the water out of the crystal structure because of all the kinetic energy. Not comfortable water. We usually, you know, when we try to desiccate things, or when we try, let's say we purchase some of this. If we purchase the copper 2 sulfate anhydrous form of that, then we have to protect it from humid air. The way we're going to protect it from humid air is by using a desiccator and some desiccant. So what does a desiccator look like? There are lots of different desiccators, but the desiccators that we have look something like this. Not exactly. Well, this is what they look like. The desiccators that we have look like this. Here. And you just put in the anhydrous calcium sulfate down here, and then this is sealed, so the air in here, being sealed in here, is going to dry out. You know, and so it'll cut down the humidity here. Of course, if you open the lid, then humid air will get in there. If humid air gets in there, then you have to give it some time to dry out. Yeah, we're going to use these. Hopefully you don't break it. It's $124 Granger, but Granger's usually pretty expensive. So that's desiccated. And so we just want to know, now how do you predict how many water molecules? Well, it depends on the crystal structure. You know, so for example, copper 2 sulfate, the max is 5, but for other crystal lattices, it's different. If we look at sodium, what's this one? Sodium, this is disodium monocarbon trioxide. Is that how I name that? Disodium monocarbon trioxide. No. What is that? This is sodium carbonate. Now, when we go buy sodium carbonate, we could either buy the anhydrous form or the hydrate. Typically, we buy the hydrate because we don't want to have to hassle with storing everything in a anhydrous environment. And so we buy the hydrate, but when we buy the hydrate, there's some extra weight in there from the water. And so when you buy the hydrated form, you're not only paying for the sodium carbonate, but you're also paying for the water molecules that get stuck in the crystal lattice, and you're buying it by weight, 50 grams. So 50 grams of the anhydrous form obviously is going to be more expensive because you're going to get more sodium carbonate versus 50 grams of the sodium bicarbonate, which has 10 waters per formula unit. But anyway, how would we name this? So let's name the hydrate. It would be called sodium carbonate decahydrate. Okay. 3 words, sodium carbonate decahydrate. Sodium carbonate decahydrate. And then how would you write the formula for this? Nickel 2 chloride hexahydrate. NiCl2, that's correct. It would be NiCl2 and then you put a dot, and then hexa is how many? So 6. 6 H2O. NiCl2 dot 6 H2Os. That's correct. And the H2Os aren't really, they just get stuck in the lattice. Sometimes they'll change the color, sometimes they won't. All right, here's a summary of the nomenclature system. So we talked about naming binary molecular compounds. We talked about naming ions and ionic compounds. We talked about acid anions and acids and hydrates. And so that's pretty basically it. I'm not going to get into the rules here because I don't follow these rules. I follow a slightly different set of rules for that. right, so are there any questions on nomenclature? Uh-huh.
So we like just go over some more of the, sorry, more of those exercises? Like,
More examples, yeah, that's what actually, this is why I had the entire lab devoted to that. And so if there's a sub, they can do that. If there's a sub tomorrow, I'll post it. They can go over it and help you. The class is canceled then. Well, the first step in nomenclatures is memorizing. There's a lot of memorizing you have to do. Memorizing the rules, memorizing the formulas and the names. Oh, am I still signing in? Alright, so I was planning to move on, but we can spend some time talking about nomenclature. I assigned the blue numbered problems with the answers, but let's try the other ones so I don't. Hide them all. Is that a molecular compound, ionic compound? I mean, what type of structure is that? Ionic lattice? Covalent lattice? Molecular? This is molecular. And so the yellow spheres represent fluorine, the green spheres represent chlorine. So what would you call this? This is FF. F2. That's the correct formula. And so that's F2, aka fluorine. FLU fluorine. Now this is a fluorine with a chlorine. If it's a fluorine with a chlorine, is that a binary molecular compound? Yes. So we just follow the rules. Now this gets a little bit tricky. Which one do we go with first? Do we go with chlorine fluoride or fluorine chloride?
chlorine.
It's going to be, you're going to do chlorine first. So it's chlorine fluoride or chlorine monofluoride. And the reason is because when we think about the anions, we'll see this pattern come up. It turns out the ones that want to be the anions the most are the ones near the top right of the periodic table. Not like helium neon, but like fluorine. And so chlorine's more apt to be the cation. Fluorine's more apt to be the anion. There are other reasons for this. In order to create ions, you have to lose electrons and gain electrons. In the formation of this, what do you think is easier to steal an electron from? A bigger atom or a smaller atom?
Smaller.
You think of maybe a smaller atom because it's weaker, but it turns out the bigger atom, yeah. Because if you look at how many electrons does chlorine have altogether? 17 electrons. How many electrons does fluorine have altogether? 9. So if it has 17 electrons, it's got a lot of electrons. So the ones that are on the outskirts of the atoms are less tightly held. Then this goes with this. Helium versus hydrogen. Which one do you think is easier to steal an electron from? Hydrogen or helium? The smaller helium atom or the bigger hydrogen atom? Which one is going to be easier to take an electron from? The bigger hydrogen atom. And the reason is because what causes it to be bigger? What causes it to be bigger is a weaker electrical attraction here, which lets the electron roam further away. Whereas this has that, what did I call that? The stronger, you like sci-fi or whatever? The stronger tractor beam, yeah. And so the smaller it is, the harder it is to take away. And so if there's going to be a cation-anion type scenario, then chlorine would be the more likely one to be the cation. So that would be chlorine monofluoride. This one would be chlorine trifluoride. D would be chlorine pentafluoride. Chlorine pentafluoride. All right, 3, 4. 4, skip that. I don't think I signed 3. Some of these others, like 6. Write the formulas of all elements that exist as diatomic molecules under normal conditions. Yeah, oxygen, O2. So that's 1. Fluorine, F2. N2. Cl2. What is? B, no, Br2. Be careful. B is boron. Boron would be single. I2. H2. O2 is H2. There should be 7 of them. There's 7 diatomic elements. 8. How would we write the formula for germanium? Does that form molecules? Or does that form lattice? Lattice. Germanium forms a lattice. And if it forms a lattice, then what's the best representation for germanium? This is what germanium looks like. In fact, it's the same lattice, so just different size atoms. This is called a diamond lattice. So carbon adopts this diamond lattice. Silicon also adopts the diamond lattice, but it looks different. And germanium adopts the diamond lattice. So what would you call it? GE. You know, you just use the empirical unit. The empirical unit would just be 1 germanium according to the diamond lattice. We don't call that a molecule. Would you call that box a molecule there? No. Let's continue on. Fluorine. What's the formula for fluorine? F2. Argon. AR. Is it AR because it forms the lattice? No. Argon, it's a little bit tricky because argon is just a atomic element. So what happens is, This is the lattice that forms. What happens is the atoms will pack together like this here, but the atoms aren't bonded together, which is different. So this forms atoms. We could have molecular and atomic lattices, which aren't bonded, which are different than the other one. And so let's compare the melting points, something like this. Copper adopts this structure. The copper atoms are held together by metallic. Actually, we'll talk about it later. Normally when we think about argon, we think about argon gas. And argon gas just consists of argon atoms in the gaseous phase. This is solid argon. So argon gas. Looks something like this.
So argon does not form molecules, right?
Argon does not form molecules, correct. So here we could have a mixture of gases. Right. Gallium. What's the formula for gallium? Ga. O2, what's the name for O2? Ca? Ba? Ag? Silver, good. Here are here you can see different elements. Carbon is at the right. Silicon's down here at the bottom. Tin is on the left, and lead is at the top. So carbon would be C, silicon Si, tin. What's the symbol for tin?
SN.
SN, and lead is Pb. CCl4. Is CCl4, is that a binary molecular compound? Yeah, it consists of two elements, carbon and chlorine. How would you name this? Yeah, carbon tetrachloride. That's the name. Carbon tetrachloride is very common in the laboratory. CCl4. What do you think it is? Solid, liquid, or gas? Solid? Liquid? Turns out it's a liquid. This is it here. It's a colorless liquid. This liquid is like oil though. It won't mix with water. So if you pour water in here, does the water stink or does the water float? The water floats on top of this. Normally when you have oil floats on the surface of water. Well, this is more dense oil. What is the density of this stuff? Let's take a look at the density. Most oils have a density less than 1. In fact, the Merck index is very good because a lot of oils are mixtures, like oil, pine oil, or etc. But the density of carbon tetrachloride is 1.58 grams per cubic centimeter in the liquid phase. So it's about 1.6 times as dense as water. And the carbon tetrachloride can stay on the bottom. Water is going to go up. Carbon tetrachloride is a class of compounds called chlorofluorocarbons. Although there's no fluorine here, this is a chloro version. These are halide, what do we call them? Carbon recognized by IUPAC as carbon tet, cleaning industry. It's halon 104 in firefighting. KL104, this stuff doesn't burn easily. A lot of the refrigerants that we use are not flammable. Carbon tetrachloride is not flammable. That's kind of interesting because there's a molecule that kind of looks like that has that same shape. Do you recognize that shape? I said that shape's a very important shape. Tetrahedral, good. There's a molecule that has that tetrahedral shape, but it's very flammable. What was it? Methane. And so something like methane, if we take these chlorines and replace them with hydrogen, it becomes very flammable. So with these chlorines, it becomes very unreactive. Carbon tetrachloride is unreactive. Although it is a mutagen, which potentially causes birth defects, it might be a carcinogen. How would we know if it's a mutagen or a carcinogen? You know, would we want to touch this stuff? Would we want to breathe in the vapor? How we need to, how we could use Wikipedia. Wikipedia, we could go to the safety section here and read it. Even though it's not very flammable, it has other effects here. Carbon tetrachloride is one of the most potent hepatotoxins, toxic to the liver. So much so that it is widely used in scientific research for figuring out these agents here. Exposure to high concentrations of carbon tetrachloride, including vapor, can affect the central nervous system, degenerate the liver and kidneys, and prolonged exposure may lead to coma or death. Chronic exposure, there's a lot of chemists who have chronic exposure because carbon tetrachloride is a very common solvent. When we're worried about chronic exposure and when we're worried about vapors, we have something called a fume hood that we work in lab. You saw those against the wall, all those boxes, those suck the vapor out. So that's what we need to use. If we're using carbon tetrachloride, we don't want to breathe in the vapors. If we don't want to breathe in the vapors, then we do the work in the fume hood just to make sure we don't. You know, there's other interesting things about carbon tetrachloride. Carbon tetrachloride is also both an ozone depleting, like the fluorocarbons are, CFCs, and it's a greenhouse gas. And its use has been on the decline. Under high temperatures, it forms phosgene. Have you heard of phosgene? Phosgene was one of these poison gases that was used in World War I. So you don't want to heat it up because it will decompose chemically into that. But, you know, in general, a lot of people say, oh, don't use Wikipedia. Well, there's an official site for this type of safety information. That official site is, you don't find it a whole bunch in the MERC. There is some safety information in the MERC, but the latest information is on the SDS. SDS or MSDS. You know, SDS is the new format that they have. And so let's take a look at the SDS form for CCl4. So when you buy a chemical from, this product has been discontinued. When you buy it from a chemical manufacturer, the chemical manufacturer is supposed to give you all the safety information here. And then you can read it and assess the risk to you here using the SDS or the MSDS. SDS just recently replaced the MSDS. And so I think they just shortened it from MSDS to SDS. So here, it looks like Aldrich, Sigma Aldrich is one of the big chemical manufacturers. They're still selling this stuff to the supplier. They have an emergency phone number if you ever need to call. Emergency. There's emergency overview. Well, I guess it is a carcinogen. Cause cancer. toxic by ingestion, and it's also toxic by skin absorption. This is why people wear gloves. They don't want to absorb some of these into their skin. Even when you do wear gloves, gloves are not impermeable. Gloves will permeate, and so there's limited lifetime for gloves. Anyway, you can read all the health warnings here. This is a good source of information. It not only gives you safety information, it gives you a whole bunch of physical and chemical properties as well. But not all the chemical properties. You know, the way the chemical properties are listed in SDS and MSDS is somewhat disorganized. And it just seems like they're hitting random chemical properties. We should have a more systematic way of representing the chemical properties, which we'll talk about when we get back to this. Well, this next one is what? This one would be carbon tetrabromide. And I would expect carbon tetrabromide to be what? Solid, liquid, or gas? I'd expect it to be a liquid. You know, maybe a solid because bromine's bigger. Maybe not, but probably a liquid. And I'd expect it to have many similar properties as carbon tetrachloride because chlorine and bromine are in the same, they're in the same family. So chlorine, fluorine, etc. in the same family. That family is called the halogens. And so these are called the halocarbons. Halocarbons, halo for halogen. How about this one? Actually, you would think that's nitrous oxide, but nitrogen is very tricky. You know, nitrous and nitric work pretty well when you only have two, but for nitrogen you have a lot of charges. What's the maximum positive charge for nitrogen? What's the maximum positive charge for nitrogen? Well, we can look that up on the periodic table. If we go to the periodic table, let's take a look. Periodic table is buried. There it is. What's the maximum positive charge on nitrogen? 5. Do you guys already see the pattern here? 5. Maximum positive charge on nitrogen. So plus 5 is it. What's the maximum negative charge on nitrogen? This is from yesterday. You write it in your notes. -3. And so what it is this. When we see this range, these are the two extremes. So nitrogen can be in the -3, or it could also be in the plus 5. And so when we look at different compounds, you know, what NO is called is not nitrous oxide. NO is called nitric oxide. Nitric oxide. You know what nitrous oxide is? N2O. This is nitrous oxide. This is nitric oxide. But that naming system is not that great because there are other species like NO2. You know, if this is nitric and this is nitrous, what would you call NO2? Nitrid double ick, something like that? Oxide? Yeah, so we start running out. You know, the ick outs works great if there are only 2, but if there are more than 2, then we're going to have trouble. And so instead of using that system, we use another system. What would we call nitrous oxide? There's other common names for nitrous oxide. If you look in the Merck index, Merck index is good for something like nitrous oxide because it deals with a lot of these. So we could look at nitrous oxide. This is the structure of nitrous oxide from its molecules. Blue are nitrogen, red is oxygen, and 2 nitrogen. nitrous oxide. Nitrous oxide is used for a bunch of different things. Food grade nitrous oxide. I don't think they use that anymore. You know what people used to do? Like when I was in maybe high school or something, people would go and get whipped cream cans and try to inhale nitrous oxide. They used to have nitrous oxide and then not anymore. Well, they have something else. I think they use nitrogen now, which isn't so great. Food grade nitrous oxide. Medicine, they use it of course for general anesthetic. And then this is recreational use. Oh, back in the, back in the old days. Yeah. Well, neurotoxicity, neuroprotection, oxidant, B12. So there's some problems. It's not all good. Ooh. Old research on it. David Humphreys is another big one. Anyway, well, that's nitrous oxide, and then we have this one, nitric oxide. But nitrous oxide, another name for that is, it's another name for nitrous oxide. Of course, you can memorize it, but if you don't want to memorize it, then usually at the first entrance. Not to be confused with nitric oxide, which has a formula NO. Or you don't want to confuse it with nitrogen dioxide either. You aren't going to laugh. Nitrogen dioxide. Or the pollutants. Have you heard of NOx? These are all NOx. NOx. Those are, NOx are formed from combustion of nitrogen. Where can you burn nitrogen? Is it easy to burn nitrogen? It's really hard to burn nitrogen. Nitrogen in the air doesn't really burn. But if you put it into a chamber, and this chamber is a very high pressure and very high temperature, you can form NOx. They call it NOx is because you form a mixture of these. You just don't form one, but a mixture depending on the condition. And so, have you ever gotten your car checked for smog? Your car, then they're going to check for NOx emissions. They're going to just combine all of them into one value. But don't try to inhale the exhaust from your car because it's probably not that much nitrous. It's probably a lot of nitric and nitrogen dioxide. Nitrogen dioxide is a brown gas. Nitrogen monoxide is a white gas. Nitrogen dioxide is the brown gas you see on really smoggy days. It's poisonous. Nitric oxide is interesting. Science Mag Molecule of the Year. Science Magazine has a Molecule of the Year, and not so long ago they did nitric oxide. When was it? Let's see. Science Mag Molecule of the Year. Here it is, 1992. In 1992, the American Association for the Advancement of Science gave nitric oxide the Molecule of the Year. Nitric oxide, you know what it is? It's a biomessenger. Biomessenger for increased blood flow. It's also used for other drugs. And then we have nitrogen dioxide here. But when we look at it, so if oxygen's -2, what does that mean the nitrogens are here? Plus, well, the whole thing is +2, but we have 2 of them. So if the oxygen is -2 and we have 2 nitrogens, what does each nitrogen have to be so that the sum total comes out 0? +1. And so this is nitrogen and the +1, it's nitrogen. Over here, you know, if we have 1 oxygen, what is the nitrogen going to be? This nitrogen is going to be +2. This nitrogen will be +4. Then we have, remember this ion? Do you remember that ion? What is nitrogen in that ion? Plus +5. +5. What's this ion called? This is nitrate. And so here we're going from +5 to +4 to +2 to +1. Right? Then we can go to 0 and 2, and then we can go all the way to this. N3-. What's this ion called? This ion is called, it's monatomic, it's an anion. Monatomic anions, you just take the element name and then change the ending. You'd like to call it nitrogenide, but nitrogenide is awkward. And so instead of calling it nitrogenide, we call it nitride. This is nitride. And so you can see it varies all the way from -3 to +5. Here it would be +5. Hey, what about pernitrate? What would pernitrate be? Pernitrate would be NO4-. That would be pernitrate. Pernitrate. Did I talk about this yesterday? No? Hey, you know what? There's no such thing as pernitrate. There's no such thing as pernitrate. Can you tell me why? Because of the charge on nitrogen. What would the charge on nitrogen have to be in pernitrate? Yeah. The charge on nitrogen would have to be actually more, +7. Is that okay, or does that exceed the max? Observe, that exceeds the max. This stuff doesn't exist. Pernitrate does not exist. However, things like perchlorate do. Perchlorate exists. There's no problem with that. And the reason is because of this historical observations. The 8 ions were the ones that they found commonly in terrestrial environment, which oxygen is present. In anaerobic environments where there's no oxygen present, then you aren't going to form these kind of species. Okay, dinitrogen monoxide is the other name for. Dinitrogen monoxide is the other name for nitrous oxide. Okay, then we have sulfur dioxide. What's the formula for sulfur dioxide? And sulfur hexafluoride. Okay, so we have sulfur dioxide, like this. SO2, what's sulfur? What would you say the charge on sulfur is? If oxygen is -2, you could say the sulfur must be +4. Is that maxed out for sulfur? No, it turns out no. SF6 is also observed. If fluoride, what's the charge on fluoride, usual charge? If the charge is -1 and we have 6 of them, that means sulfur must be +6. Would you expect something like this, sulfur decafluoride, to exist? No, because that would bring it up to +10. And if you look at sulfur, sulfur should have a max positive charge of No, 7's wrong.
Plus 6.
Maybe I need to show you the periodic table, but it's we'll do the periodic table. Yeah, here you can see it a little bit better because sulfur is below oxygen here. Is it 16? 6. This would be group 6B, or 6B or 6A? That would be group 6A. Okay. All right, let's take a look at some more of these. Okay, I skipped this section here. What are the formulas of tin 4 ion? And okay, what's the formula for tin 4? SN 4 plus. Manganese 3. Mn 3 plus. Now Pb2 plus, is that variable charge or fixed charge? If it's fixed charge, we just call it the lead ion. If it's variable charge, we would call it lead 2. So which one is it? Lead 2. Cobalt fixed charge or variable charge? Variable. So that would be cobalt 2 ion. We don't need the word ion, because that the Roman numerals can tell us it's an ion. And so what are the formulas for nickel 3 oxide? Okay, when I do the formulas for this, I just write the ions first and then figure out how many I need. There are other methods that people use. And so let me show you the two most common methods. If I have nickel 3 oxide, then this is nickel with a 3 plus charge. What is oxide? O 2 minus. And right now I have excess positive charge. I don't have enough negative charge. And so in order to get more negative charge, I'm going to add another O2 minus. But now I have too much negative charge, so I'll add another nickel. But now I have too much positive charge, I'll add another oxide. Now it's okay. Plus 6, minus 2, 4, 6, minus 6. Plus 6, minus 6, it all balances out. And so this is going to give me 2 nickels and 3 oxides, Ni2O3. Okay, the other common way that people do this is if you have nickel 3 plus and oxide 2 minus, people take these numbers and use those as the subscript here. And so this would give, it's like cross multiplying, Ni2O3. It's the other way.
Does that always work?
It works, but sometimes you have to do an extra step.
What's that?
The extra step is like this. If I have manganese 2 oxide, and I did this, there's a problem. You get, 2O2. That's not right, because manganese 2 oxide is an ionic lattice. We don't have a molecule, Mn2O2, right? And so this is not the empirical formula. So the extra step is we have to get this in the simplest whole number ratio, MnO. So yes, it works if you adjust it at the end. Okay. Lithium nitride. What's the formula for lithium nitride? Well, what's the charge on lithium? It's in group 1. So it's got to be +1. And what's the charge on nitride? Nitrogen ion with a negative charge would be
5 or negative?
+5, but it can't be plus because it's IEE ending. It's got to be negative 3, so we call it 3 minus here. And so how many lithiums am I going to need? 3. So I'll have Li3N. That balances out the charge. Chromium 2 chloride. Let's try that. Chromium 2, what is the Cr2 plus, and then chloride, Cl minus. So figure out how many do I need of each. 1 chromium and 2 chloride should do it. So CrCl2, chromium 2 chloride. Aluminum phosphide. This aluminum is a fixed charge. What's the charge on aluminum? 3 plus. Phosphide is the phosphorus with a negative charge. What is the negative charge on it? Minus 3. Or 3 minus. And so this is where, if you did the subscripts here, you'd have to simplify. This is just a simple 1-to-1 ratio, ALP. Okay, name this for me, MnF3. Well, first is manganese. Manganese variable or fixed? Is manganese variable or fixed? Manganese occurs here, element number 25. Variable or fixed? Variable. And so that means this should be manganese with what charge? 3, yeah, good. This is manganese, Roman numeral 3. And so the name of that would be manganese, open parentheses, Roman numeral 3, close parentheses. That's all one word, manganese 3. And then the anion is trifluoride or just fluoride? Fluoride. It's just fluoride because if we know the charge on manganese, then we know how many fluorides are required to balance it. So if we added tri, then it's just, yeah, repetitive. It's redundant information. It's not necessary. What's the next one called? Well, Ni is nickel. Is it variable or fixed charge? Variable. And so what's the charge on nickel? 2. And so this would be nickel, Roman numeral 2. Now nickel has a number of spellings depending if you use British English or American English. What is the American English spelling? British English spelling is like this, Nickle. But the US, we spell it like this, Nickel. But I don't care which one you use. Honestly, you can use
Like
either.
color.
Yeah, like color. Right. And so this would be nickel 2. You need the Roman numeral 2. And what's the anion name? Sulfide. The D clues me in. It's monatomic. The next one is very tricky. Next one is very tricky.
How do you know when we change the ID?
The second element gets changed.
Like when do we use the other ones? Like 8?
8.
Yeah.
When we have a T, it means what element is present. If there's a T, it means that we have what element in addition present. If it's a D, if it's a T, we have 2 choices. We have ite and ate. What's the difference between ite and ate? Oxygen. And so when we have a T, there's oxygen present. Here, there's no oxygen. We'd never call this sulfite because there's no oxygen present. Sulfite is SO3. People get them confused all the time. It's SO3 2 minus. That's sulfite. Sulfide is S2 minus. Sulfite and sulfide. This one we wouldn't use 8 or ite either because this is monatomic. This would be called, well, this is tricky because I don't know if that is this. Is that oxygen gas? O2 gas, the gas we breathe in air? Is that an oxygen gas stuck on a piece of lead?
I'm assuming not.
And then, like the lead brick we had here, you could just suck the oxygen off the brick. Then if you go diving and you run out of oxygen in your tank, just take the lead weights off your belt and then suck the oxygen off the lead weights. Does that work? No, even though the lead weights are probably heavily oxidized, you aren't going to be able to suck the oxygen off the lead weights. because that oxygen is not oxygen gas. What is that oxygen? So if we have PbO2 like this, that oxygen is something else. That oxygen is, well, we have a Pb and we have two oxygens like this, and each oxygen is 2 minus. And therefore, lead must be, it's got to be 4 plus. And we would call this lead, because lead is variable charge, we call it lead Roman numeral 4 oxide. But there is a chance that there's one more anion that could trick you. And the one more anion that could trick you is this. It could be a lead and an O2 2 minus. Have you seen an O2 2 minus?
Yeah.
Yeah. O2 2 minus is called peroxide. And so if it's an O2 2 minus, what's the charge on lead now?
Plus.
It's going to be 2 plus. And so we can't tell if this is lead 4 oxide or lead 2 peroxide. Can you? No, you can't tell. Right. Except, so you're going to have to know some additional knowledge. If you buy some hydrogen peroxide from the supermarket or wherever, does it last forever? Now, what do you know about peroxide? Are they stable? You know, there's a story. It's kind of an interesting story. There was a gardener, and they use peroxides for soil conditioning. Have you heard that? And so this gardener got a great deal on some hydrogen peroxide in LA. I think it was in LA, and wanted to bring it back home in Northern California. And so this was pre-TSA days. So what this gardener person did was he convinced the baggage check-in to take it. What he ended up doing was he got a Coleman cooler, ice chest, put the hydrogen peroxide in the ice chest, and then closed the lid, and then taped it up. But what ended up happening is the hydrogen peroxide started leaking out of the container, and then when it came into contact with the fabric luggage, it caught on fire. And so, this is the story. There are a number of stories like that. And so one thing you know about peroxides is that they're not very, actually, was it in Florida? My memory's not good. I thought it was in California. I think it was in Florida.
Sounds like Florida.
Yeah, Northwest Flight 957, 1998. 2 gallons of 35% hydrogen peroxide. Well, anyway. So one thing about peroxides is this bond here. You know, this is what we call a bond. Peroxides are all unstable. You know, they're all going to decompose. And so, you know, it's much more likely it's this. Because if this were lead 2 peroxide, it's not very stable. You have to watch out for this stuff. And so, in all likelihood, that's lead 4 oxide, not lead 2 peroxide. All right, how about the next one? The next one, we could use our little trick. Our little trick is reversing this. And so we use the 3. This has got to be cobalt plus 3, and this has got to be sulfur minus 2. Do you see that little trick we do? And so this would be called cobalt Roman numeral 3 sulfide. The easiest way to learn nomenclature is just do a lot of practice problems. And so this is why I assigned so many problems in nomenclature. What element is present? And did I tell you when I was at UCLA what some of the classmates were doing? They weren't doing the problems that were assigned. They were doing all the problems. Every single problem in the book they were doing. Why? They wanted that little competitive edge. So, anyway, 26. What element is present in all acids discussed in this chapter? No. Like, for example, hydrochloric acid. Does hydrochloric acid have any oxygen? No.
Oh, no, hydrogen.
Yeah, hydrogen. Remember, the cation's always the same. Yeah, so. Oops, I forgot about the break. We'll take a break now. And we'll start again. During the break.